So it's time to start again. Welcome everybody. My name is Manolis Koubarakis. I'm the session chair for this first tutorial of ICD 2020. The tutorial is on the topic of machine learning and big spatial data. And it is given by Ibrahim Sabek and Mohamed Mokbel. They are both experts in big spatial data and machine learning. Starting with Ibrahim. Ibrahim was a PhD student of Mohamed in the University of Minnesota until recently. He has done his PhD in exactly this area that the tutorial is about. And actually his dissertation won the University Dissertation Award from the University of Minnesota. And Ibrahim is now a postdoctoral fellow at MIT, working on similar topics like the ones that the tutorial is about. Mohamed is the chief research scientist of the Qatar Computer Research Institute and also a professor at the University of Minnesota. He's very well known for his work in spatial databases, especially on big spatial data. And he has received a lot of awards like best papers and things like that in this area. This session will be run exactly as the previous session, the keynote by Johannes. So feel free to ask questions by using the Q&A functionality, and I will pass them to Ibrahim and Mohamed. With this, I would like to pass to Mohamed for starting the tutorial. Mohamed will start, and then Ibrahim will continue. Thank you very much.
Okay,
Mohamed,
thank you.
over to you.
Thank you, Manolis, for the introduction. Thank you, everyone, for coming online. Looking forward to meet you in person in the near future. But for now, I think online is our best bet. And thank you, Bhavani, and everyone, the ICD organization committee. Doing this in a couple of weeks, I couldn't believe that they would be able to do it. So that's very good. Excellent. So the topic of our tutorial, machine learning meets big spatial data. I will walk with you for the first 20 minutes of the tutorials, 20 to 30 minutes, and then Ibrahim will go on next. My job is to make it more of a teaser for you or to convince you why we need to think about this topic and why there's a big gap in the machine learning and big spatial data, and show you opportunities there. Ibrahim is going to detail more into existing techniques and state of the art, and where can we go from there. Start by what is the rise of machine learning. It's not something that I need to convince you about. You have heard machine learning everywhere, and if you just look at the rise of machine learning in different fields, this is just some articles, not research articles, more of magazine style. You find in Forbes, rise of machine learning and AI in improving lives, the rise of machine learning in cybersecurity, rise of machine learning in astronomy, in different fields. So everyone now is like looking around for how to use or how to deploy, to exploit machine learning for their fields of interest. One of my favorite quotes by Google CEO, when he said, machine learning is a core transformative way by which we are thinking everything we are doing. Meanwhile, as someone working with big spatial data for long, it has become ubiquitous. All of us now are aware about mapping, routing. We use spatial data as some kinds just granted around us, and new technologies, startups working with it. And even if you go for a bigger scales and using your own location data and finding your route around, existing of satellite data, even medical data like X-rays is treated in a spatial way. Social network uses the spatial data. So it becomes around us in a way that becomes ubiquitous, and we don't feel really about it something new. Also just 10 years ago or 15 years ago, you wouldn't even care about much of this spatial data. The question now, can we use the machine learning for big spatial data? And if these two creatures got married together, what's going to happen here? So we have plotted this kind of diagram here. On the horizontal axis, we're thinking of machine learning fundamental algorithms, where there are non-spatial machine learning algorithms and there are spatial machine learning algorithms. And in the application side, again, on the vertical axis, I have non-spatial application and spatial applications. And in fact, most of the things we look around for using machine learning, I would classify it as belonging to the same quarter, which is you develop machine learning fundamental algorithms and you develop non-spatial application for them. And most of the algorithms, a large majority of them, think of spatial data as just one more data into your equation. Why should I differentiate between non-spatial data and spatial data? I'm just doing my algorithms, my techniques, my system that deals with data, and that's it. If you're going to talk to me about spatial data, yeah, just use my algorithm and it will work. My job in this tutorial is to convince you that this is not enough. Do not think of spatial data as the same as non-spatial data. Spatial data has its own characteristics and its own things that needs to be treated spatially and spatially. And I will show you different things here. In particular, I'm going to talk about these three other quarters. I'm going to motivate these three other quarters for you, and Ibrahim will detail more techniques. And three other quarters, what does it mean to have a spatial machine learning fundamental algorithms to non-spatial applications? Or the other two quarters here. And also, what does it mean to convert non-spatial machine learning algorithms and techniques to be spatial one? And does it worth it or not? Is this something we want to investigate, want to look at or not? So let me start as a motivation with this quarter here, which is basically spatial machine learning fundamental algorithms for non-spatial applications. One of the very common applications for machine learning is knowledge-based construction. And when you think about knowledge-based construction, most people think of it, okay, what is the spatial thing has to do about it? I know how to do my knowledge base for any kind of data. And this is what people are using mostly. So what is the process of knowledge-based construction? Basically, you have your box of knowledge-based construction system. Your input is a set of articles, PDF articles, websites, Wikipedia, whatever you can get as an input. And then a set of rules. And these rules apply to the document you are given, that apply to the input documents. And out of these rules and documents, the main role of a knowledge-based construction system is to extract relations and then produce a table of relation of what they consider facts. For example, you can make a spouses knowledge base. From these documents and these rules, you can say that person 1 and person 2 are married, like Barak and Michelle are married. That's you are extracting a fact or you are constructing a knowledge from unstructured documents. Okay, and then came the field of probabilistic knowledge-based construction. So it's not a knowledge-based construction per se, but you add the probability to it. And this is by another module called factual scores inference. And the difference here is that when you report a knowledge base, when you report a knowledge, you report it with a probability of being correct. For example, here in the spouses knowledge base, we can report that Barak and Michelle are married with 0.85 probability, 85%. And Joe and Katie are married with 52%. Joe and Lily are married with 46%. Then the interpretation of this probability is left to the user, how to interpret this probability. But at least the knowledge-based construction here is not giving you things that as facts or not, it gives you more as a probability. This went, a lot of systems came out of probabilistic knowledge base, a lot of systems from industry and academia have worked into this with a lot of valuable input and systems that are widely used. In fact, maybe the most common one or the most recent one is a DeepDive system that came from Stanford, and it has been really used in human trafficking and geology and different things. And in fact, you can even find CNN, Forbes articles about it. And Apple acquired dark data specialist lattice data for $200 million, which was based on DeepDive. So DeepDive in general is one of the most, or the state-of-the-art system for probabilistic knowledge-based construction. When we look at DeepDive from inside, this is how it looks like. DeepDive, which is a machine learning-based knowledge-based construction, it's built on scalable implementation of what's known as Markov logic networks I don't have to go to you in details here, but it has a language module, grounding module, inference module, and so on. If you look at the word spatial here anywhere, there's nothing. And the question is, why there's nothing? Maybe it doesn't work, you know, I mean, or maybe everything here can work in spatial the same exact way like it works with non-spatial data. So we got DeepDive, we installed it, we played with it, Ibrahim gained really good expertise about how to work with DeepDive. And then we said, okay, we're gonna give it some problems that we know it has spatial factors. So we tried DeepDive with spatial data with this real example. We have 4 cities in Minnesota: Minneapolis, St. Paul, Eagan, Rochester. And these 4 cities, we know the education level of each city, which is 0.7, 0.7, 0.7. They have the same education level. This is kind of real data. And we know that the city of Minneapolis has high crime rates. And then we want to use DeepDive to know the crime level of the 3 other cities. So here are the rules, inference rules we give to DeepDive. A predicate 1 says city X has high crime rate. Predicate 2 says cities X and Y have the same education level. And the rule is simple. If P1 and P2, which means if a city has a high crime rate, and if 2 cities have the same education level, then Y would have high crime rate. Same like X. That's the simple rule. We apply DeepDive here, we get this answer. Because we have the ground truth, this is not an accurate answer. This is a pretty inaccurate answer. We thought about it, why DeepDive is not working here? And the simple answer is, okay, you know what? If you are in an interactive session, I will ask you to answer this question. Okay, let me go on. Here, is crime data is a spatial thing. If 2 cities are neighbor, they are likely to have similar crime rate. If 2 cities are neighbor and have the same education level, they are more likely to have the same crime rate. So we said, okay, this is what we can do with DeepDive. I will add a 3rd predicate. Cities X and Y are within 80 miles. So now I have 3 predicates. If predicate 1, predicate 2, and the predicate 3, all of them are valid, then Y would have high crime rate. What does this mean? This means if the city X has high crime rate, then X and Y have the same education level, and X and Y are within 80 miles, then Y would have high crime rate. And now we injected the spatial thing into the rules given to DeepDive, which we run DeepDive here, we get another difference than the one before. It's more accurate, it's actually more accurate, but it's not good too. It's not good either. This is not what we should get. We should get really better answers than this. We replicated this algorithm, this technique on a different data sets. We get Ebola infections later in Liberia when Ebola was a big thing at the time. So these are 4 counties in Liberia. And these 4 countries, we know the sanitation level at the 4 countries, 0.6 for each one. And then we know that the first county has high infection rate. We want to know the other 3. So we exactly did the same. Predicate 1, county X has high Ebola infection rate. Predicate 2, counties X and Y have the same sanitation level. And the rule, if P1 and P2, then Y would have high infection rate. We apply this to DeepDive, we get an answer, which is not accurate. Our interpretation, DeepDive does not understand spatial data, or sorry, we did not express spatial data in rules. So we did a 3rd rule here. Counties X and Y are within 150 miles. And the predicate is, if X has high infection rate, then X and Y have the same sanitation level and within 150 miles, then Y would have high infection rate. We did it again in DeepDive, we get better answer, but not accurate. Usually I would ask a question here, why you think it's not accurate here? And let me come up with the answer. The answer that this thing is here are not accurate is that you are expressing, or we are expressing the spatial functionality in the rule, not in the engine. Yes, we did a spatial function here, or yes, we did spatial predicate, and yes, DeepDive allowed us to put a spatial predicate, but this spatial predicate did not make it to the engine. And why this is bad here? Because when you say cities X and Y are within 80 miles, this is so rigid to spatial data. Because now you are saying, if a city is like 75 miles, then this predicate is true. If a city within 85 miles, then this predicate is false. but 75 and 85 are not far from each other. And actually 85 is like 80 here with respect to distance. So the reason is that DeepDive deals with predicate as 1 or 0, which could be okay for non-spatial data, but this is not okay for spatial data. Again, DeepDive deals with predicate and give an answer either 1 or 0. It's okay for non-spatial data, but this is not acceptable for spatial data. Spatial data is a different treatment, because what you want to say, the farther the city is, the lower probability it would be, not to put a rigid thing, it's either 80 or not. So what we wish to have is this rule here, predicate 3, the one marked in green now, I scratched the red one and put a green one. This is what we want to do. We want to do predicate 3, the closer y and x together, the higher y crime rate. And again, the Ebola thing, the closer x and y together, the higher y infection rate. This is the predicate we want to have. And then one applies the rules at the 3 predicates. However, doing this DeepDive would not work, because the answer to this rule is a spatial answer, which has this gradient, cannot be 0 or 1. And DeepDive cannot support this. So what we need here is to go inside DeepDive and look at the machine learning modules and let it understand the value of spatial data, or the unique properties and unique characteristics of spatial data. Once we are able to do this, DeepDive would work well with the rules with spatial data. So this is just an example here, just a motivating example for the need to support spatial data. Even if you think of a knowledge base, okay, knowledge base has nothing to do with spatial. No, it does. In fact, I'm not sure that there is anything now that has nothing to do with spatial. And I have another talk called Thinking Spatial, which is advocate for these things here. But to us here, this is a motivating example, is that if I can support the spatial data in the machine learning algorithm, DeepDive or anything else, okay. So I made a teaser now for the first missing quarter here, which is spatial machine learning algorithm for non-spatial data. Okay, I will go now to another quarter, which is non-spatial machine learning algorithm, the traditional machine learning algorithm, how to use it for spatial data. Okay, and I'll give you an example of routing. What is routing? This is the most fundamental applications that we are almost using daily, right? I want to go from my home to the airport. I want to go from my home to work. I want to go visit my friend. I just put my GPS and let it tell me where should I go. So how many routing algorithms, how many routing calls you call every day? A lot of them. So routing is a big fundamental operation in any kind of spatial, in the spatial data. And in fact, the number of companies that are based on routing are huge. Started from ride-sharing companies to just mapping like Google Maps and Apple Maps and different things here. And how routing work, basically, you have source and destination, and then you have the routing algorithm. Routing algorithm takes 3 input, source and destination, and takes a map, and provide you routing. And there are tons of techniques of how to do routing. In fact, there are techniques now, which is actually mostly used in commercial things, is that you pre-compute the routes for most things. And when someone asks about source and destination, we give you the pre-computed route. Okay, routing to me is a premier example of the disconnection between industry and academia. Most people in academia, and you still can see this in papers in VLB, Sigmund, IZE, SIG Spatial, and all first year conferences, you can steal papers working, inventing new routing algorithms. I would really call to stop this. I mean, there's no need for doing better routing algorithms. Well, everyone is not looking at the routing. All industry actually is looking at the map. Why? Because you know what? If you have the best routing algorithm ever, but you have a wrong map, your routing algorithm would give me garbage, even if it's the most efficient routing algorithm ever. And if your routing algorithm is not the most efficient one, but acceptable in performance, and your map is accurate, your map is good, you will give me much better route. And guess what? I mean, all the battle now between industry is on the map, not on the routing algorithm. It's all about the accuracy of the map. And this, you don't take it for granted that the map is accurate. This is not true. In fact, the map is about 2 things. If you take the map, think of it as 2 things, topology and metadata. What is topology? Topology means the road segments. of your map, okay? And you can argue, okay, your city has the best coverage all over the world, that's fine. Other cities are not. But even if your topology is accurate, what is more important is the metadata of the map, which is very hard to say it's accurate. What is the metadata of the map? Metadata of the map, for example, what is the weight of this road segment? If you have a road segment on a highway in a rural area next to your home, to the map, to the routing algorithm, it's a road segment plus a weight. A weight means the distance, the time takes to pass this road segment. And by the way, this cannot be a single number, as simple as this. If you put a simple number as a weight of the edge of the road network, that's wrong, because this number changes from day and night, changes from weekends to weekdays. So you really sometimes, I mean, some of our experiments, we did like 168 numbers per edge. So figuring out the map, the topology, or the metadata, machine learning can play a major role here. I'm sorry. Ibrahim will go with you in details on different techniques that use machine learning to come up with the map. Once you get the map right, now you can go ahead and apply your favorite routing algorithm. I'm not going to tell you which routing algorithm you will apply, because the map is accurate now. And for example, I give you, there are many articles that say, for example, Google Maps leads about 100 drivers into a muddy mess in Colorado. Another article, Google and Apple Maps have plenty of errors. It's all about maps. But then I have this table, this huge table that compares Google Maps versus Apple Maps versus Waze versus MapQuest. These are 4 common applications that people are using for routing. And I think there's more than 40 factors comparing Google Maps, Apple Maps, Waze, and MapQuest. None of these 40 factors talk about routing. They talk about the quality of the map, the accuracy of the map, more the interface, different things, but not about the routing, because it's done. That's why I still feel bad when I see papers coming field, D segment, ICD, especially talk about routing algorithms anymore. So anyway, machine learning can really help us here in coming up with better maps. And we'll show you detailed example. Ibrahim will go with you in detailed examples here. Okay, so now I want to give you a teaser about the third quarter here that was not covered before, which is having spatial machine learning fundamental algorithms for spatial applications. So we have 2 spatial things here. And I'll give you an example of a spatial regression, or what's called autoregression here. A spatial autologistic, it's called autologistic regression, which is basically a spatial autologistic regression. It's find whether a spatial phenomena exists or not based on neighbors, values, and features. It has tons of application. This is a classical problem, decades old problem. It has been there for 20, 30 years or something, which is basically weather prediction, birds migration, different application. And the whole idea looks like this. If you look at the grid here, each grid has a value 0 or 1. 0 means this phenomena exists. 0 means that this phenomena does not exist. 1 means that this phenomena exists. And this phenomena could be, there's rain here at the cells with 1, no rain at cells with 0, and so on. And then each cell has what's called features. Like you see, a first cell here has X1 and X2. So each cell here has 2 features. These features could be the humidity level, could be the shade, the vegetation of the thing. So each cell has a value, either 0, 1, and the feature, whether this feature exists or not. And if you see at this grid here, there's a cell I14 has a question mark, which means it's missing. And what autologistic regression do is basically predict or find out what is the missing values here. Okay. One thing you can say, okay, missing value, I'm going to interpolate. No, that's not what a statistician do. And I'm not here to argue what is the best way to fill in this value, because there is already an equation for this. And I did not come up with this equation. You see this logarithmic equation. I did not come up with this equation. This equation has been there for decades. Spatial statistician came up with this equation. And basically this equation, try to find the missing value, and Z here is the missing value I'm looking for. The probability of this value equal 1, equal so and so. What I want to show you here is that this equation really rely on 2 regression parameters, theta and eta. Actually not 2, many parameters here, because eta is 1 parameter, but pj, that could be in our example here, there are P1 and P2 because we have 2 features. If we have more features, it could be more and more. Okay, the job of all spatial statistician is to use the values that is completed here to feed in this model and come up with the values of the regression parameters. Then when they have the value of regression parameter, now they can apply it and find the missing value. Okay, this solution has been there for long. However, learning regression parameter for like something like 80K cells, which is not big, that could take more than 1 day. It's very expensive to do this equation. It's very expensive to solve this equation. And as a result, people who are doing spatial statistics start to use this equation, but not to use fine-grained cell. So let's take for every 8 cells, make them as 1 cell, and so on. So they simplify the problem a lot to find solutions, and then it's not going to be accurate. What I want to show here is that this is an open problem for machine learning people, because you can use machine learning to solve this equation in a very, very scalable way. And Ibrahim will go with you in details about this. So I'm done with my part here. My job was to motivate you and to some kind of an eye-opening to show you that using spatial data and machine learning can open things that we did not think about it as solvable before. I will stop sharing here, and Ibrahim will share his screen and continue from here. I'm still alive, so I'm still online, so I can answer questions with Ibrahim anytime.
Okay, so I'm gonna share my screen here. So can anyone hear me?
Yes, sir.
Okay, great. So hi, everyone. My name is Ibrahim Sabir. I'm going to continue with you the rest of our tutorial today. Basically, I'll go through the details of the different techniques in each quarter that we have in our landscape. Give the main idea, describe some detailed examples and applications. And after that, I'll give an overview of the end-to-end systems that support spatial data and machine learning together. So let's start with the first quarter that we have here, which is spatial algorithms for non-spatial applications. And the main theme here in this quarter that, as Professor Mokber mentioned, that we have non-spatial applications, and we want to make sure that the existing machine learning algorithms used inside these applications have support for spatial awareness so that we can have a better performance at the end. And we are gonna start with the first example that we have here, which is knowledge base. And as a quick recap for the knowledge base example that Professor Mokber has shown before, we use DeepDive, which is one of the most popular knowledge base construction systems to build knowledge bases from spatial data. And we still found that we have some limitations in inferring very accurate factual scores. Actually, they were not that accurate given the spatial properties that we have in our data. And this is because DeepDive, for example, doesn't have a support for the predicate B3, as Professor Mokber mentioned before, which is like the closer Y and X is a higher Y crime rate, because this kind of predicate support the gradual semantics needed for the spatial applications. And DeepDive doesn't have this spatial support. So to resolve this issue, one of our work recently on the knowledge-based construction systems called SARE, we proposed in this system to add the spatial awareness inside the different components of the knowledge-based construction system. And basically, we started to work with the internals of DeepDive, which is built on top of a popular framework for machine learning called Markov logic network. I'll give details about Markov logic network later in this talk. And we started to have a spatial variation of this Markov logic networks. And using this variation, we built a very powerful spatial aware knowledge-based construction system. And as you can see here, this is like the high level architecture of our SARE system. We added the spatial extensions in the different components like language, grounding, inference. You can see here we have spatial data types and functionalities to allow the people to express the semantics of their spatial problems. And also in the grounding phase, we added some spatial SQL query supporting for constructing the knowledge-based relations from spatial data. And also in the machine learning core itself, used inside the knowledge-based construction system, which is about the inference, we added a spatial aware inference algorithm called conflict-based sampling, and it was very powerful for inferring the factual scores of the spatial relations that we have in the knowledge base. And by doing this, we got more accurate performance numbers in the factual scores using, say, compared to DeepDive. Going back to the same examples that we had in the motivation, you can see here in the green scores that we had much better confidence scores compared to the one that we have in DeepDive. And if you are interested in more details about SEA itself, you are welcome to attend our presentation on Thursday, research session 21. We have a paper there, and we are gonna give more details in our presentation. So now we are gonna move to another application here in this quarter, which is about image analysis. And basically we are looking for the problem of object detection in images. So basically you have an image and you have some objects in this image that you want to detect. For example, you have a handwriting letter like O here in this input image, and then you want to detect it. And traditionally this problem has been solved with traditional deep learning approaches like convolutional neural network. And actually they are performing very well, this kind of approaches. Well, they are dealing with dense cases like images with dense objects and this stuff. However, it's surprisingly not performing so well for the sparse cases. And specifically if you are running on a low resource device like mobile devices, because it's very computationally expensive. And the idea here that some people come with a very efficient idea. So instead of like using traditional convolutional neural network, we can borrow some spatial partitioning techniques like Quadtree to remove any unnecessary computation during the process of computation of the convolutional neural network. And by doing this, they are making sure that all the different layers of the convolutional neural network pipeline, including the convolution itself, rectification, Boolean and upsampling, and so on, all of them are compatible with the Quadtree. And for example, here, if you can see, this is like kind of image. And while you are going through the high resolution layer of the neural network that we have here, we can focus only our computation on the gray parts that are coming from the Quadtree partitioning. And now we are ignoring anything here in the white space. So this will save both like storage and time costs and make it very efficient. So this is like another example of how we can take a very popular algorithm like convolutional neural network and make it very spatial aware and using technique like Quadtree, and then we become very efficient in the processing and in the storage cost. Another example here we're gonna show also in this category is event detection. And in this application, we detect events based on a sequence of social signals. Basically, we can use the tweet counts that we can observe within a certain time period and within a certain region to give us a sense if there is any abnormal event is happening or not. And traditionally, this problem also can be solved using neural network. And one of the successful approaches has been used extensively to do this is long short-term memory recurrent neural networks. However, this kind of approach, if it's used by itself only, it's focusing only on the temporal aspect more than the spatial awareness. And it generates kind of bias in the results. And to resolve this bias, we combine something like spatial convolution with this LSTM networks. So now we embed here convolution filters with some spatial information during the process of like our constructing neural network here. And by doing this, we come up with more accurate results at the end. And this approach called convolutional LSTM, and it started to be very popular in the spatial domain since 2018. So this is also another kind of application to embed the spatial awareness inside the construction of the neural network itself and how to process the different layers of the neural network. Last example here in this category that we have here is recommendation system. And basically a recommendation system is an engine that analyzes the user behavior to recommend interesting things and interesting items. So basically in the recommendation, the recommender system starts to gather some information about the user item ratings and build a recommendation model out of these ratings, and then use this model to answer any user query about recommendation and give us some inputs, some outputs here. And one popular approach is to build a collaborative filtering algorithm based on factorized matrices. And although this algorithm is very popular and have some like success stories in different commercial products, the problem here that also it's still missing the spatial dimension that can be important also for the recommendation quality. For example, people in the same area could be interested in the same thing. We can think of this like if people in the US could be interested in watching some kind of movies, like they are really interested in action movies, for example. But if we think of this like in the Middle East area, could be like people interested in another kind of movies. So having the spatial dimension in the recommendation quality itself could be very beneficial. And to solve this, people started to add the spatial and temporal correlations across the user and items used in building the collaborative filtering approach. And one of the things here I'm sharing, one of the very popular work in 2009, they added some spatial regularization terms for the user and items while building the model itself. And by doing this, they have achieved more successful recommendation results. So in conclusion here, we just covered few examples of adding the spatial awareness inside the machine learning algorithm used for the non-spatial applications. And of course, these applications or like these examples that we just talked about are not all the examples. In fact, we are encouraging people to start like moving some applications from this quarter, the non-spatial applications for or non-spatial algorithms for non-spatial applications, to move kind of these applications to the quarters that we just talked about by adding some spatial awareness inside the algorithms used. For example, in digital health and cybersecurity, people can start like thinking spatially on how to add the spatial dimension to optimize performance, as we did in knowledge base and image analysis applications. So now we're gonna move to the second quarter that we have here in our landscape, which is specifically for non-spatial machine learning algorithm for spatial applications. And the main theme here in this quarter that we wanna make sure that we use existing non-spatial machine learning techniques. And in this case, we are using the machine learning techniques here as is, as a black box, without any spatial addition inside them, to efficiently solve long-lasting spatial problems. And Professor Mokbel talked about one of these applications, which is routing. We're gonna give more details about the routing application and also give details about other applications like traffic prediction, outdoor localization, spatial object detection, and forecasting. All of this kind of spatial applications, core spatial applications we need in the spatial domain, and all of them are making use of the non-spatial machine learning algorithms as is. So we found also in the most of the recent work in this quarter focus only on deep learning approaches with few other state-of-the-art classical approaches like classification and cluster. So we gave like some examples on the different applications as we move on. So we start here with the routing application. And a quick recap also, as Professor Mokbel mentioned, it's not only about routing algorithm itself, it's also requiring having the correct maps. And also this includes having the correct topology and correct metadata. And also we are gonna give some recent advances in both of this, like metadata and topology making for having correct maps. So we start here with the topology making itself. So for topology making here, we are gonna cover a couple of works here. And basically the first work is route tracer system. And basically in this system, they are trying to construct route maps from satellite images. And they are using some machine learning techniques to do this. So basically in this problem, classical machine learning approaches are called, in this case, segmentation approaches. They try to classify the pixels in each image, whether it's belonging to a route or not. We found that, and also like the people in this like routing area found that this could have some high error rate if we have like some messy satellite images. And in this approach, which is using neural network here instead of like having classical approaches like classification or regression, they started to have much better performance by using iterative search process guided by convolutional neural network. So they start to incrementally build the route, or like the route segments that we have, point by point. And this implementation process is guided by convolutional neural network. So they search point by point using convolutional neural network. And as you can see here from this example that we have, this is a final output coming from the segmentation methods and the root tracer methods. That you can see here that root tracer can have much better performance in detecting some challenging routes like bridges, like turns, and this kind of stuff. And this proved the efficiency of using convolutional network, even if it's not spatial aware, using it as is in some kind of applications like topology making. Another kind of work also for the topology making coming from Facebook AI, and they are providing something very cool called Map with AI. They are also using the convolutional neural network, but in a different way. They are using it to extract very improved features from high resolution images. And this feature will be used to build very accurate classification approaches, like have very weakly supervised learning classifiers, but now based on very improved features. And as you can see here, this is like the output on the right-hand side here, the output from the Map with AI. And it's very, very accurate when we compare it with this output coming from the segmentation methods also. And even people now started to combine this kind of approaches with OpenStreetMaps and to get more and more accurate results. So the main message here in this approach is that also using the convolutional neural network can improve the feature extraction also used for classification or regression in the spatial domain. So now we are moving to the metadata part. So we just covered two works for the topology making, now for the metadata part. And in this problem, we assume that we have the root network, like we have here the segments, but now we don't have the weights, and we want to predict them. And traditionally, these weights are estimated as one number, but as Professor Mokbil mentioned, it should be accurate if you are estimating this based on time granularity, different time granularity, because it could be different from rush hours than like night hours. So you need to have specific time granularity when you are estimating these weights. And in this work, instead of like having fixed value for each weight, we are they are like in this approach here using some Residual regression analysis to predict this time granularity based weights. So basically here they have the input as a set of trips. Each one of this trip could have like the pickup time location, drop off time location, and the pass. And after that, they are constructing a set of linear equations out of these trips, as you can see here. For example, this from trip from B to H. And then we have like a linear equation based on the weights that we have here in this trip. And after doing this for all the trips that we have, we end up with having X equations in Y unknown variables here. And the problem here is transformed to solving these equations within like this unknown variables. So the first step here is starting to use the dimension reduction methods to reduce the number of equations and reduce the number of unknown variables. And then we pass this equation and unknown variables to a very classical approach for regression analysis called regression analysis. And by doing this, we can have the edge weights per granularity. This is like an example from the Qatar trips case study there. And we have here, for example, 10K equations in 500K unknown variables. After the dimension reduction, we can improve this by having only 1K equations in 5K unknown variables. And then for our granularity, we can have edge weights per hour. So here we are using a classical regression analysis, not like deep learning, for also detecting the metadata weights that we have. Another kind of work also focus on detecting this weights, also coming from ICD 2019, and it's focusing on sophisticated weights. More than having like one weight per each time granularity, we can also infer a distribution, like a speed distribution for each certain time granularity. For example, here we can have this like root segments, and the edge weight here is instead of like having a weight like W as we had in the previous slide, we can have a distribution here. So for example, here at a certain time granularity, we can say that the probability of having speed like traffic speed between 5 and 10 is 0.3, and those from 10 to 15, for example, here is 0.5, and so on. Of course, this kind of detailed information is not available for all root segments. So the problem here that given this few known like speed distributions, can we infer or predict the missing ones? Like, for example, here in our example, we have the speed distributions for E5 and E6. Can we use them to infer the speed distributions for E1, E2, E3, E4? And the output should be something like this. So the solution here starts by putting this kind of speed distributions that we have and the adjacency matrix that we have between the graphs into a suitable format for the neural network solution. And then we apply graph convolution operation on this like input data that we have. And basically here in the graph convolution operation, it's similar to the convolution neural network, but now instead of having like the traditional filter, we have this filter based on each network node and its neighbor in the graph. So based on the neighborhood in the graph. And after that, we can apply the traditional neural network pipeline and get the completed weights at the end. So the main message here also that even we can use the machine learning to infer more sophisticated weights, not like only one number per each time granularity, but also we can use this with a speed distribution or like inferring distribution at different time granularity. So now we're done with the metadata and topology making. Just for completeness, we are gonna give also one recent advanced machine learning based routing algorithm. And it's also coming from ICD 2018. And the interesting part about this routing algorithm is that it introduced a new concept for routing, which is like learning how to route. So basically, you can define the features that you are using for having a good route. For example, here, you can say that other than the distance functions that we can usually use for like having best routing algorithm, we can use, for example, route condition, like whether the route that we have or this segment is ready or not, if there any work construction in this part or not. And by defining these features, you can have an opportunity to learn more personalized routes for each user. And the solution here that given a complete route network, now we have the route segments and we have the weights for these route segments and some trajectories as inputs here coming from the trips, for example. First, they are starting to cluster this route network into something called region graph. So now we are trying to group some nodes in the route network and like try to construct a region out of these nodes. And after that, we learn some preferences for the trajectories in each region. And if we have some trajectories that are missing some preferences, we can also transfer the preferences from one trajectory to another if they have a high similarity. And this similarity can be user defined. After that, we have a complete set of trajectories with learned preferences. And whenever we have a user query based on the source and destination, we can recommend, based on the learned preferences for these trajectories, we can recommend a suitable route. So here we are using classical approaches like clustering, learning approaches like regression or classification. Even with this simple and the classical approaches, we can also achieve very sophisticated routing approaches. So we're done now with the routing applications. We are gonna go through another application, which is traffic monitoring and prediction. And traffic monitoring and prediction is a very classical problem in the spatial domain. However, existing solutions before this like big era of the deep learning approaches were focusing only on the short-term prediction, like prediction for 20 minutes only, or maybe less than this. But now with this recent advances in the machine learning, people now started to question the long-term prediction, like can we like predict for days, for months, something like this. And we're going to give some examples here for how we use deep learning for, or like in general, like advanced machine learning approaches to do this prediction. Specifically, we have 4 examples. So let's start here with the first one, which is using the residual networks. Specifically, they are using here a combination between the convolution and the residual networks. Like this is a variation to handle both spatial and temporal dependencies. And in this approach, they are just getting the traffic input maps and divide them into different time spans. And in parallel, they are applying this pipeline of the convolutional residual networks on each one of these traffic maps. And then the results of the prediction are fused together to get the traffic prediction. And in this approach, we can find here that also having this convolution based on spatial filters can improve the performance of the spatial results that we have for the traffic, because at certain parts, if you have a traffic with a high rate, you can have also like, you can infer that, or you can make sense that also the areas around this part or this region could have also high traffic rates. And without having a specific convolution that can capture, convolution filter that can capture this spatial semantic, you cannot have accurate traffic prediction. A second approach here is using also a variation of that convolutional recurrent neural network, which is called diffusion convolutional recurrent networks. And the main idea here is to consider the pairwise spatial correlations between the traffic nodes. Like for example, if we have traffic sensors deployed and we are getting information from each other, so how can we capture the spatial correlation between these traffic nodes? And in this approach, they are modeling the problem as a graph problem, where we have the traffic sensor node as the nodes in the graph, and the edge weights between these different nodes capture the spatial correlation. Now we need to do a convolution over this like graph that we have, but now while considering the inflow and outflow traffic that we have. And to do this, most appropriate approach is to do the diffusion convolutional recurrent neural network. For example, here, we can start from a node here at iteration theta 0, for example, and we do convolution based on this node and its neighbors in the graph. And in the next iteration, we start going from the neighbors that we already convoluted was in the first iteration, and we do this over and over in the different iteration until we cover the whole nodes that we have in the graph. And after that, we combine like the all results that we got and get the prediction at the end. So basically here also, this is like another example for convolution recurrent neural network used for traffic prediction. Another work also using something called lookup convolutional recurrent neural networks. And also now, instead of using the spatial correlation between the traffic sensor node, we try to adapt an algorithm that captures the root network itself, the whole root network, like the whole root segments, and how to incorporate this inside the convolutional process in the traffic prediction itself. And the main idea here that for this like root networks that we have at certain time granularity, we generate a feature vector, and then for different time granularities, we have different feature vectors that we are gonna use inside the convolutional process. And after that, we got the prediction here was like an overview of the root networks that we have. So this approach is very efficient in capturing the spatial correlation also among the different nodes and the different root segments at the end. So the fourth approach here, and this is the last one for the traffic prediction, is using reinforcement learning. And basically in this problem, they are trying to focus on controlling the traffic lights and how to do this. Because it's a very important component in the traffic prediction. And doing this using a standard deep Q network, this was like recent work from 2018. They started to use the Q network to build an agent policy from the traffic training data that we have. And after this model is built, we can use it with any traffic input in the future And then given this traffic input data that we have, we generate some agent actions that say that how we control the traffic lights. And to get some feedback after a certain time period, we can collect all the the traffic lights control signals that we got and see if they are matching the actual results that we have, or improving the condition of the traffic prediction at the end. If not, we are going to signal it back to the DeepQ network to relearn the agent policy again based on new set of traffic input data. So this is another example of using reinforcement learning for traffic prediction. Now we're moving to another kind of application here, which is outdoor localization. So basically here in this application, we want to localize the people using their phones and without any GPS signal. And main idea here that we can get a fingerprint using the received signal strength from the cell towers and without using the GPS itself. So the approach here is having two phases. The first phase is the offline phase, which is training. We collect some lat-long information associated with the cell towers that we get and the received signal strength. And once we get these fingerprints, we can build a localization model. And building this model could be using any advanced neural network application, or also using any standard or typical classification model. After we do this localization model building, we can, in the online phase, get also the RSS values only without having any lat long. And then we detect this lat long, the estimated locations that we have based on the localization model. Another application here, also very famous in the spatial domain, is quality forecasting. And specifically, one of the applications is air quality forecasting. So at a certain location, within a certain time period, we want to predict the quality. And usually we can do this using hybrid regression models to separately deal with the spatial and temporal correlation. However, more sophisticated approaches are recently proposed, specifically from Spatial 2018, based on convolutional neural network to capture these spatial and temporal aspects jointly. And this leads to more accurate results. And also they are following the usage of another variation of diffusion convolutional recurrent neural network, similar to what we have in the traffic prediction. Another, the last example that we have here in this category is detecting the spatial objects inside images. And by detecting this geospatial objects, we mean that, for example, if you have an input image like this, and we want to detect the buildings from images, for example, or detecting cars or whatever, something like this from the images. It's very challenging because sometimes these objects are not aligned to the X and Y axis. And existing techniques could be confused if you don't have this. Sometimes it can have wrong answer, or sometimes it can give you a very approximate answer based on the minimum bounding rectangle. But now, thanks to the recent advances in the machine learning approaches and convolutional neural network, specifically the YOLO convolution approaches, we can get more accurate results and specifically get the actual shape of the object. As we can see here in the output here, the detected object, we can get the actual shape of the object, not like the minimum bounding rectangle, using something like multi-layer YOLO convolution. And the details, of course, are omitted here because we don't have time, space for this. So by concluding this applications that we already talked about in the second quarter that we have here, we have shown that also non-spatial machine learning algorithms, mostly here in deep learning approaches, can be used as is to solve this spatial application. And also it makes sense because machine learning algorithms could be also useful if we don't have the spatial variations. Now we are going to cover the third quarter that we have here, which is basically about having specifically spatial machine learning algorithm designed for spatial data analysis applications or spatial applications in general. And Professor Mokben mentioned one of them, which is a spatial regression. We're going to cover also other topics like spatial classification, spatial Bayesian, spatial sampling. Of course, there is a wide range of applications and algorithms in this quarter, but we are gonna focus on the recent advances here, just to give you the taste of what's happening in this quarter only. So we're gonna start here with the spatial autologistic regression. And as a recap, we have the issue here for this spatial autologistic regression for the scalability. The regression parameters, in case of having large scale data, can take so much time to be like accurately inferred. And this is a problem well known in the spatial domain. And what we did here is that we invented a new solution, which is very, very scalable based on the Markov logic network, similar to what we already discussed in the DeepDive solution in the system says that we have already implemented. And basically, we are using a spatial variation of this Markov logic network. So now we have a specifically designed Markov logic network for spatial applications and used it for some spatial problems like spatial regression here. And we're going to see the details now. So basically, before we start about talking how we solve the spatial regression, what's Markov logic network in general, just for the people who doesn't know about it. So if you know, like this, there's a common problem in current machine learning approaches, which is machine learning is not that user-friendly for different people. So not so many people can use it. Specifically for deep learning, it needs experts and highly trained scientists to implement it, write lots of code and do some hyperparameter tuning. So it's very sensitive and not so many people can do it. And Markov logic network is specifically designed to alleviate these problems. For example, here, it can be used to express the problems that we have in a very few number of logical rules. And this solution of the Markov logic network is covering a wide range of the statistical learning and inference approaches. And basically, this Markov logic network is coming from University of Washington, introduced by Pedro Dominguez there. And since then, it started to be used inside different kind of applications, and it proved its powerful nature to solve the problems. And recently, it's scaled up by Quadtree from Stanford and implemented inside some applications like DeepDive, as we have shown before. So what we have done here is that we built a spatial variation of this Markov logic network, because Markov logic network itself is not very equipped for the spatial data. The example that we had in the knowledge base like showed this like limitation. And what we did here that we added this spatial extensions to the stack of the spatial to the stack of the Markov logic network, as we discussed before. And by doing this, now we are ready to solve different kind of spatial applications or analysis algorithms, like spatial regression, and spatial classification, and spatial Bayesian network. Now we are going to focus only on the spatial regression, because this is like kind of application we are talking about. So how to use it, how to use this like spatial Markov logic network to solve the spatial regression problem. So basically, we are getting the regression equations, the autologistic regression equation, and pass it to a transformation module that transform this equation into a set of rules that can be used with the spatial Markov logic network. And these rules should have some weights, and these weights should correspond to the regression parameters that we wanna predict. And by passing it to the engine and solving the problem and solving the prediction for these weights, we are solving the problem for the regression parameters. As a specifically, this is like one example here, specific example. We have here an autologistic regression model for a grid of 4x4 cells. We only have one prediction variable and one predictor variable, which is x1 here. And we have here, for each cell, we have the neighbors coming from the vertical and the horizontal cells. So basically here, Z4 having its prediction based on the different neighbors here we have, which is Z2, Z7, Z10, and Z3. So we just pass this equation to the transformation module, and we come up with a set of logical rules here that connect between the prediction variable that we have Z and the predictor variable, which is X, as you can see here, Z and X, connected by some bitwise and operators. And most importantly here, these weights of the prediction and predictors are also embedded here in these rules, which is like beta 1 and eta, corresponding to this weights in the regression problem. And after we do this transformation, we pass it to the spatial Markov logic network engine, and then we learn the parameters of beta and eta. And while we are doing this, we are solving the scalability issue, because Markov logic network is much scalable, more scalable than the existing and traditional approaches in the regression. So we move now to another spatial analysis problem, which is Bayesian modeling. And this problem here, it's very common, and it's used for analyzing the spatial data in general and estimating its parameters. And the module that we have here for the Bayesian is similar to the traditional regression equations that we have, but now we have Gaussian process assumption for the error terms that we have here. And most probably here, the problem coming also from the estimation of the parameters, like what we had in the spatial autologistic regression. We cannot infer the correct parameter values in a very efficient way for large scale data. And specifically, if we are gonna go through the inference process, the distribution now will include more parameters to be inferred. And now we have, instead of having 2 parameters that we wanna estimate, we can have more parameters to be estimated, like more additional 3 parameters. And to solve this problem here in Bayesian modeling, one of the recent approaches is Quadtree-based Bayesian modeling. And they are proposing that instead of having one likelihood estimation for all the parameters that we have, we can exploit a decomposition approach where we can estimate these parameters on different partitions, and then we try to combine this estimated parameters. And of course, this could be like an approximate approach, but it started to prove its efficiency if we have larger scale data. So now we can see here that we have these different parameters during the inference of the posterior, like what we have here in the last slide. Here, the Bayesian inference, we have here C and M capital. So these parameters could be inferred here from the different partitions separately, and then we can approximate these parameters together at the end. And this approach is called meta-cracking, and started to be popular since 2018. Now we move to another application here, which is a spatial classification. It's very similar to the traditional classification problem that we usually aware of, but now we are doing this within a spatial context. So for example, here we have, similar to the traditional classification, we have training images which are labeled with predefined spatial classes as input. And the input here is that we have another image that we don't know the labels, and we want to predict the labels here. For example, here we have some pixels forming a spatial class, like what we have here in the brown, and also another class which is like the green here. So we need to have this spatial coherence between the different pixels. And this problem also started to be non-efficient in terms of getting accurate, in terms of getting fast response of the classification result when we have larger scale data. And this started to be solved by trying to abstract the way that we classify the spatial data. And now we do this by doing an approach called super pixel classification. So now instead of doing pixel by pixel classification, as traditionally is done in this kind of spatial applications, we start to group the objects in a form like superpixel, and this superpixel is still conserving the main properties of the spatial object itself. And after that, we pass it to the feature generation module along with the training image to get more accurate graph building for the superpixel classification model. And then we build a classifier that can generate the labels at the end. And when we have an input image, we can get like this spatial classes at the end in a very efficient way. So now here, the main message in this approach is that we can use some kind of abstraction like superpixel classification to improve the performance of the classification itself. Another approach is ensemble learning spatial classification. And it's very similar to the general ensemble learning. Basically, you are dividing the problem into different subproblems, and then we build a learner for each of these problems, and then we ensemble the output at the end for both of them. For example, here we can have like one image, and this image has two different zones. And for each zone, we can build a certain classifier, for example, a decision tree or something like this. And then we combine the results here in a more sophisticated way to preserve the spatial properties, to have like one final output at the end that represents a classification input that we need. So this is like also another borrowing idea from the ensemble learning, spatial classification. So the last application here in this category, or like the last problem that we are tackling here, is the spatial sampling. And it's very common if you have like large spatial data, you cannot like afford working with the whole data points that you have. So you need to select some representative samples from the two-dimensional, for example, if we have like working with maps or like any spatial domain, we need to have some representative samples from this domain. And we have a bunch of algorithms here like random, stratified random, systematic, and also systematic aligned approaches. All of these approaches are good, but now they show some bias if we have large scale data. And we had to use some machine learning approaches to get more accurate spatial samples in these cases. And one of the approaches here is to do this sampling in an incremental way, not like doing it like a whole iteration, but we can do this on different iterations. And we start by getting some sample, and then we get some feedback from the user, and then we store this sample once it's approved within a certain data structure that's very efficient for changes and updates for the different samples. And by doing this, we stop after the different iterations you specify as a user, or after you reach to a certain acceptable ratio for the accuracy. Another approach here, which is like the last one that we are gonna talk about, the spatial sampling here, using deep learning also to learn the spatial samples. And basically it builds a deep network. And this deep network can be used to preserve the original shape. So to sample some data points while preserving the spatial shape. Like for example, in 2D objects inside images, we can have more representative samples. And in the testing phase, these generated samples could be matched with the input to estimate the error for feedback. So basically it is used for kind of spatial applications combined with the computer vision application. So by like concluding this example in the third quarter, we now completed the overviews that we have on the landscape of the machine learning intersection with the spatial data. We have 3 quarters, as we mentioned, and we have shown here that machine learning can be beneficial for spatial data, and spatial data can be beneficial for machine learning. And we can pull techniques from different like worlds to improve the other world. And we encourage people to start like moving applications from the third quarter to the different 3 quarters that we have here, and optimize the performance to have better output at the end. Now I'm moving to the last part here quickly, which is like giving an overview of the end-to-end systems for machine learning and spatial data at the same time. For example, here the first stack that people started to use extensively in the recent days is Spark-based spatial machine learning systems. as we all know, that Spark now is very booming, and it has successful stories for the spatial data management also. We have so many systems like GeoSpark, SEMPA, GeoMesa, and people started to integrate this within the machine learning pipeline. So basically, they are expressing the spatial machine learning operation using Scala language, and then generate some plans that can be using some operations from the Spark machine learning library. And then after that, if we need anything related to the data management or spatial data management, we can use any spatial Spark core layer, like one of these systems, to make this computation during the machine learning processing is very efficient. And another system here also very common is PyCAL. It's an open source based on Python, and people started also to have some increased interest in this now because now people started to work with Python very commonly. And specifically, this tool is very designed for the spatial data analysis algorithms like clustering, hotspot detection, outliers detection, regression analysis. And it's not very equipped for the deep learning approaches. So if we have a deep learning approach that we want to implement with the spatial data, PyCAL is not the very first option to do this. Also, another system we have developed ourselves, based on the spatial Markov logic network that we have shown before, specifically designed for probabilistic graphical models. And we can use it to build any kind of this graphical model, like a spatial Markov random field, spatial hidden Markov models, spatial Bayesian networks, and also still not equipped for the deep learning approaches, because Markov logic network itself is not equipped for expressing the deep learning approaches, but can solve equivalent problems. Another system here is GeoDA, which is specifically for exploratory spatial data analysis. It's a very visualized system, and it has a nice visualization nature if people want to do some interactive data analysis for the spatial data. And recently, it has some cloud-based computation versions that can support very large scale data. Before that, it was limited for the desktop application, but now it started to be supporting larger scale data. And of course, ESRI also is a big giant in the spatial domain, and they are providing two different tools recently. One for deep learning called GeoAI, and can be used for deep learning, classification, clustering, regression, anything for these operations with the spatial data. And another tool called GeoAnalytics, which is for the traditional data analysis operations over spatial data. And they have also recent version, which is supporting the distributed computation for scalability. The last system that we highlight here is IBM PAIRS. And its main edge is that it's one of the key players in the cloud-based service for the geospatial analytics, specifically designed for big spatial data, and can handle like complex queries at real time. So it has also successful stories for weather prediction and started to be used commonly among different people. So by doing this, we just conclude our observation about the synergy between the machine learning and big spatial data. We see that a lot of opportunities coming from the intersection here between the machine learning and big spatial data. And still we have some issues that we need to resolve or think of to protect this synergy, like privacy issues, ethics policies, and any kind of other problems that can come up with from the intersection of these two worlds. And by highlighting this, I'm concluding my talk, and thank you everyone for your attention, and we're happy to have your questions. Thank you.
Thank you, Ibrahim. Thank you, Mohammed, for your very interesting tutorial, and also for keeping to the time that we have allocated. So let me now thank the people that have posed questions. I will pass you the questions one by one. I'll start from the last one that just arrived. What if you have to connect temporal data with spatial data? How would you deal with that?
Yeah, so I can talk about this. Yes, that's an interesting. We try to solve the spatial part first. We did not look at the temporal part, and I'm not aware that there are many things there. I think it's our first step is to look for the spatial stuff, but definitely temporal is next. And I would say that it's not going to be a trivial extension to go from spatial to spatial temporal.
Okay, so you will follow the traditional approach, let's say, Mohammed, right?
Yes.
Yes. Okay.
Okay. We had a lot of work in spatial big data, and then we moved to spatial temporal. Yeah, it's not a trivial extension, and there's not much work there. And I think we're starting to scratch the surface of doing things with machine learning with spatial data. And yes, we're going to look at temporal next. Yes.
Okay. The next question is the following. We normally think deep learning models like CNN and LSTM, we normally think that they can learn and utilize spatial/temporal information automatically. Do we still need to extend these models to spatial data? If yes, what type of extensions are needed?
Yeah, I can answer this or elaborate about this question. So basically, yeah, we definitely convolution neural network and this kind of like specifically the convolutional based approaches are specifically designed to capture the locality, and they are introduced for this like reason in the image analysis at the first place. But as we have shown, for example, in traffic prediction, we need to design a specific filter or like specific way of like connecting the information between different nodes based on route segments, for example, or for example, like in graphical convolution, we can take into account the neighborhood information. So it's not like the traditional convolution neural network. You need to do some extensions based on the spatial constraint that you are specifying. For example, for the traffic prediction, or for example, in the routing, you have some constraints that you need to extend the filters that you have in the convolution neural network to be more efficient in these cases. And in these kind of papers that we have highlighted in the tutorial, they have done this. Like they started with doing the traditional convolution neural network, for example, with its default spatial filters, and they found that it's still having some limitations. And then they design more filters or like more specific things to do this.
I can add to this here, generally speaking, not only to CNN, the ability of utilizing spatial temporal information has different meanings here. One meaning, for example, is that I'm going to support it from the data types only. So I will just add spatial types, and that's basically my support for spatial data. That's not everything. Another meaning is that, oh, I'm going to consider the locality between points, either as a time series, for example, that is a temporal locality, or as points neighborhood to each other. And then, because I'm considering locality, that's everything. No, that's not everything. There's deep in the system yet that these points that are localized need to be stored together and indexed in a way that provide more efficient. So there are always techniques that utilize the spatial or temporal information at one level of the stack. But what we are calling for is that you may need to think of the whole stack together. Yes.
Okay. Thank you, Mohammed and Ibrahim. Let me check here the questions again. An interesting question that just arrived is the following. Have you faced problems trying to find big spatial data sets for applications related to traffic prediction and trajectories? If so, how have you dealt with them?
Okay, so there are some available datasets online. I agree it's not large. It's working in QCRI in Qatar. I'm lucky to have access to all taxi data in Qatar. We have access to them as a live stream. So I can get all the data coming from all taxis, and that's really big data and very valuable data. I know that other people in other small countries like Qatar have some similar access. In US, you don't have this. There was a public data set, New York taxi data, but that's not really as large as it should be. Yeah.
Okay, thank you, Mohammed. Another question is the following. What new challenges do machine learning and deep learning algorithms raise to spatial data processing and access methods?
Yeah, so basically, what I found in the literature survey here that we have done for this tutorial, that so many approaches like machine learning and deep learning approaches are used to enhance the performance for spatial data analysis operations, not for the spatial data access method or like spatial data management operations. And the only thing that connects between the data accessing or like data partitioning and the machine learning approach is what we talked about, for example, in the first quarter, the Quadtree partitioning thing for like convolutional neural networks. So now they are using these access methods for improving the performance of the machine learning or deep learning approach. But I'm not aware of anything till now like using the machine learning to like fundamentally improve the access methods that we have in the spatial data. So of course, there's like some recent work on learning multi-dimensional indices, for example, in Sigma, or like trying to borrow the same ideas that we haven't learned indices also in the spatial data, but still like not like many approaches are now beating the current state-of-the-art approach. We don't know exactly if they are so much efficient or not. We're still like under investigation. So not so many approaches about this now existing.
So if you look at the recent Sigma VICD, I mean, the ones that like this year and last year, there's at least 5 or 6 papers talking about auto learning index for spatial data. Following the paper about learning index, like the B3 learning index, people have followed with the spatial data. But to me, that's like one trial to mimic something that happened for learning index, but not as a system or not going through the whole stack. Like there are projects now, and I think Ibrahim is participating in one of these projects, is how to have a whole stack of machine learning to fit databases or systems for machine learning. This is missing in spatial data.
Okay, thank you both. There are 2 more questions that I would like you to consider. The first question is whether you could talk a little bit about the spatial factor graph that you mentioned in one of your slides. I suppose you will have to go back to that.
Yeah, so basically, I don't know if the time will allow us to give more details about this or not, but basically in the spatial factor graph, what we mean is that it's a variation of the factor graph. So factor graph is a way of constructing the relation between random variables that we want to apply any learning and inference operations on them. And the way they are using here, that they are not considering the spatial correlation between the different variables. So if you have 2 logical variables, you can represent them using the factor graph. But you don't have any way for the vanilla factor graph or like the traditional factor graph to represent the spatial correlation between variables. What we want to do in this, or like what we are proposing in the spatial factor graph, that even if you have these 2 variables connected logically, they also can have some spatial correlation between them, and we can add some spatial factors specifically designed to capture this spatial semantic. So that's what we mean by spatial factor graph. And if the listener is interested in more details about this, we're going to talk about this also in our session on Thursday for the details about SEA. So we're going to describe in detail how the spatial factor graph looks like.
Okay, thank you, Ibrahim. And one more question, which is probably related to SEA as well. In the knowledge extraction example with which you started the presentation, Mohammed, I suppose, started the presentation, you said that DeepDive cannot handle the spatial questions because they don't have binary answers. But the statements P1 and P2 that you showed were about education level and crime rate, which also don't seem to have binary answers. Can you expand on that a little bit?
No, they actually have binary answers, because the predict one says that an education has high crime rate, and this is either 1 or 0, whether it has high crime rate or not. And the second one was that the two cities are have the same education level, and that's also the answer to it is either 1 or 0. And maybe here the interpretation of have the same education level doesn't have to be 0.705, like say exact, maybe within some factor. The answer here is 1 or 0. And then when we add the spatial rule, like two cities are within 80 miles, that has 1 0. So in fact, the predicates were binary.
Okay, okay. Thank you for answering this, Mohammed, as well. So let me close with the last question that we have, which is the following. How can causality be handled between different spatial data sets? For example, taxi data and weather data, particularly with tools such as Flash and PyCAL.
So, so I can talk for Flash, for example. So we have implemented the spatial Bayesian network, for example, like probabilistic graphical model for handling the causality itself. So Bayesian network itself is handling a graphical model to handle the causality, and also we implemented a spatial Bayesian network which is handling also the spatial correlation and causality at the same time. So it's a very well-known probabilistic graphical model, and what we have done in Flash here that we just implemented the approach, the traditional approach, but now in a scalable way. So as a short answer here, causality can be handled with an approach like spatial Bayesian network. And by using Flash, we can have a scalable approach like this. I'm not sure if PyCAL can be used to implement this approach or not. I'm not aware of any probabilistic graphical model is implemented using PyCAL, but I need to double check this. Yeah.
Okay, thank you, Ibrahim. I promised that this would be the last question, but there is one more which is really interesting, and I would like you to consider this as well. Could you elaborate a bit more on both future research directions and challenges related to both big spatial data and machine learning?
Yeah, okay. So I think it was part of the main part of the tutorial is putting this kind of classification of spatial and non-spatial data. Once you start thinking that spatial data is different than non-spatial data, this opens a huge, open a lot of directions for future research things. For example, and I usually take it from the application side. There are a lot of application side in spatial data that you can think of using machine learning for them. And from the other side, which is practice, honestly, I always do with my own PhD student, is that we get a system that is running already, a system that is very well used, and just try using it in spatial data. Most likely, you will find that the answer is not satisfactory, because usually the system designers usually think of spatial data as an afterthought problem. That's usually open a lot of things here. Another thing is, like one asked before, the temporal part is really missing. It's not in the picture yet. So this could be immediate future things.
And if I can add to what you answered, Mohammed, and then you also know how to write the paper, right? Because you start by saying what the problem is with the current system, and then how you solved it. So it's a really exactly. Nice way to look at that. Okay. So let me.
Yeah, this was really an excellent tutorial. I was here for most of it, and I found it very useful. Thank you very much.
Thank you, Wafak.
Thank you.
And on behalf of the organizers, I would also like to thank Professor Manolis Koubarakis, who is himself an expert in this area, for expertly running the session.
Thank you.
Thank you. So allow me to thank Mohammed and Ibrahim one more. We can clap electronically or in any other way. We can stop here. I would like to thank the people that asked the questions and all the other participants as well. Now there is a break, and then we go on to the second keynote.
Right, and
So
that will be in the same room, right? The webinar room, the second keynote. Right, it's going to be in the webinar room, I believe. Yeah. Thank you.
Thank you.
Thank you.
So the student worker, I think we need to stop sharing the screen, right? So that, right. Okay, thank you.